Hi, in this video, we want to take a look at the properties of the least squares estimate of the coefficients in linear regression. Okay, so first thing I want to say is that there are tons and tons of ways that we could actually come up with parameter estimates, coefficient estimates for a linear regression model. We could have lasso, we could have ridge regression, we could have Bayesian regression, and of course least squares, the one that has been in all of these videos. All right, so all of these have advantages and disadvantages. If we're interested in theory, the least squares estimate is by far the juiciest, easiest to work with. So it's a good choice for the purpose of theory, for hypothesis testing, stuff like that. You know, and we can derive a lot of the properties about it. So what we're going to do, we have a model, and our model is that the model value of y is equal to an estimated intercept plus estimated coefficient times our first predictor variable, estimated coefficient times our second predictor variable, and down the list all the way through to our last predictor variable times its estimated coefficient. All right, so remember that we have three assumptions about this. Well, first of all, that we have the model structure. Second is that the expected value of the residuals is 0. We have constant variance, and when I say constant variance, it means that the x values do not change the distribution of the residuals in terms of variance. And let's see, we have independent observations. All right, so that's those are the three things that we need to be able to do to approach this type of modeling for hypothesis testing. Now, one thing that we will also tack on when we need it is that we'll make the assumption that the residuals are normally distributed. Okay, so when we're in the situation that we want to do least squares estimation, we want to be unique. First of all, we want the solution to exist. We want the solution to be unique. All right, so really the main thing that we need for that, so if we look at this formula, the big thing that we need from this formula is that we need this inverse to exist. Remember that, you know, I'm going to have predictor variable data. I'm going to have a target variable data, like those we get for free. So this X transpose Y is not a problem. Over here, inverses don't always exist. All right, so it'll work out that if the inverse of this matrix exists, then the coefficients, the estimated coefficients, will exist and be uniquely defined. Okay, well, what if there's no inverse? Something we have to worry about. Well, in that situation, there will be estimated values that will minimize the least squares, but they won't be unique. So we're going to be looking at that. So when we're talking about this inverse existing, we need our X matrix. First and foremost, we want to have at least as many rows as we have columns. And remember, when we talk about columns, that's all of our predictor variables plus the constant one column. So that's the first thing we're going to need. Also, we need X to be full rank. If we don't have full rank, this inverse will not exist. And the rank is going to, since it's going to be full rank, will be the number of columns, which will be equal to 1 plus our number of variables. And so far in linear models course, we haven't said anything about the statistical properties of these coefficients to any real extent. So now let's go ahead and start digging and let's start thinking about it, because up until now, really, we've just been talking about geometry for this type of modeling. Well, first thing that we always talk about in statistics when we talk about random variable is the expected value. Then we start talking about variance, covariance, stuff like that. And then we start digging into usually the distribution from that. All right, so the expected value of y is equal to x times beta. So realize that we don't know what beta is, but we know what x is, and we have observed y values. Then the expected value of beta hat from this formula is equal to beta. This means that beta hat is an unbiased estimator of the coefficient vector. Okay, so how do we prove this? Well, the expected value of beta hat is the expected value of this matrix multiplication. Now remember that we are making the assumption that all of our X observations, all of our predictor variables are not random. They are observed values. And since they are observed, and we're assuming that they are perfectly observed, that they're perfectly measured, I should say, that these are constants. Well, if they're constants, I can go ahead and pull them out of the expected value. So when I do that, I get everything involving an X out of the expected value. You always want to get your X out, right? You want to get your X out? Get it? Get it? Okay. All right, well, what's the expected value of Y? Well, from this assumption up here, the expected value of Y is X times beta. Okay, so let's replace expected value of Y with X times beta. Okay, let's do that. So now I see that I have X transpose X, and I'm multiplying by its inverse. Well, that's the identity matrix, right? Anything times its inverse is the identity matrix. Boom. And we get beta by itself. Easy peasy lemon squeezy. All right, let's keep on going. Feeling good, feeling good. All right, for the next theorem, we're going to talk about variance and covariance. Always in statistics, we start with expected value, then go to variance, then we go to distribution. That's just kind of like the name of the game for us. All right, so if the covariance of Y is sigma squared times I, all right, so there's a lot in that little sentence right there. That means every single observation of Y has the same variance. Okay, that's a big deal. Covariance is 0 between all of the observations. And, you know, that is a big deal. So that's not quite enough to say independence, but in the case of the situation of normally distributed, it will be. But, you know, covariance equal to 0 is a big deal for us. All right, so when I have this diagonal matrix, is my covariance on Y, then the covariance of my coefficients is going to be the sigma squared here times the inverse of X transpose X. Okay, so let's do the proof. All right, so I need a covariance of beta hat. All right, well, using the formula, that's just, you know, this part, X transpose X inverse, X transpose Y. So the covariance on that. Now, I realize that once again, the X matrix is a constant. All right, well, it's a constant. That means that I have a formula from chapter 2 that I can apply. I'm going to go back to chapter 2. I'm going to grab that formula, and I'm going to slap it down right here, right now. All right, so I apply that formula. I take the X, put it out front. I take take all the X stuff, take the transpose, and put it over here. Okay, so now I've got the X's up here in the formula. The X's up here in the formula, transposed. And in the middle, I have the covariance of Y. Well, by assumption, we know the covariance of Y is this diagonal matrix. Okay, well, this is a scalar times the identity matrix. Scalars commute in matrix multiplication. So that means I can pull that sigma squared out front. Now, multiplying by the identity doesn't do anything. Well, if it doesn't do anything, I can just get rid of it, right? All right, so at this point, all of this becomes all of that. All right, I see that I've got this X transpose X inverse, X transpose X, X transpose X inverse. Well, if I multiply 2 of these, it'll cancel out to be the identity. And so then I just kind of ignore it. And so then I'm left with the result. Isn't that nice? Isn't that beautiful? Okay, so let's say we're in the situation where the expected value is something else. Let's say that maybe I have a biased estimator. Maybe there's a biased value for one of the coefficients, something like that. If it's a, you know, just if I'm in a situation where the expected value of Y is not X beta, then the expected value will just be this. And that's basically just following the proof and just stopping early, not applying the assumption on the expected value. Well, I could also do the same thing with the covariance. If I go through this proof, if I know the covariance of Y, but it's not necessarily a sigma squared times I, let's say I don't have 0 covariance. Well, then this formula will give me the covariance of my beta hat. All right. So these formulas, basically, whatever the expected value of Y is, this is what the expected value of beta hat will be. Now, in the vast majority of situations, we just kind of assume that this is what we really want it to be. So it works out nicely. And this is one, and right here, for this to work out, is why we keep on saying constant variance over and over and over whenever we're talking about the assumptions in linear regression. Okay, so let's go through and let's work out the simple linear regression examples of these formulas, just to make it a little bit more concrete for us. Now, in the situation where we have more than one predictor variable, the relationship gets a lot more complicated really quickly, because you'll notice up here, almost all of the time, I'm not going to have zero covariance on my coefficients. So that's something to be mindful of when we look here. That if I work this out, unless I have orthogonal columns on X, it's going to work out that, and orthogonal isn't necessary, but it is sufficient. It's going to work out that we have non-zero covariance. Okay, so that means that, majority of the time, if I increase one of the coefficients, another coefficient is going to adjust to kind of keep things equaling out the way they work out. And that will come to bear when we talk about variance inflation factor later down the road. Okay, so let's do simple linear regression. All right, well, the expected value of y is x times beta. I'm just writing it out right here. The covariance of y is sigma squared times I. Okay, so the expected value of our hats are what we want them to be. And our covariance, well, I know that it's a beta sub 0 hat variance, beta sub 1 hat variance, and then the covariance on the off diagonals. Well, using the formula, I know that these guys equal this. All right, well, let's go ahead and let's compute what this bad boy is. Well, x transpose x, if I think about it for a bit, remember that the first column is all ones. When I take one, the vector times itself, the dot product, I'm going to get n. When I take the one column times the x vector, I'm going to get x bar times n. That gives me both of these. And when I take this vector times, or dot product with itself, I'm going to get the sum of the observations squared. All right, well, this is a 2 by 2 matrix. We have a beautiful, wonderful formula for the inverse of 2 by 2 matrices. So let's go ahead and apply it. Easy peasy lemon squeezy, boom, we got this. Okay, well, I know that this inverse times sigma squared is equal to this matrix here. So if I go through entry by entry, I can line it up. Now it works out that there's another formula to represent this part down here after I do a little bit of manipulation. It's going to be the sum of square deviations from x bar. So applying this, I know that the variance of the y-intercept is going to be this ugly fraction right here. The variance of the estimated slope is going to be sigma squared divided by the sum of deviations of x from x bar. And then the covariance is going to be sigma squared times the predictor variable average divided by that sum of squared deviations. Okay, so one thing to think about is if I'm in a situation where I get to control what the x values are. So like, let's say I'm in a design of experiment situation. Well, what I can do, if I set it up so that x bar is equal to 0, then I know I'm going to have 0 covariance between the intercept and the slope estimates. That's very nice. Also, I notice that if I want to minimize the variance, I want to make sure that this term down here, the deviations from the sample average, are as large as possible. All right, and then that will minimize the overall variance. This part up here, this is an assumed value that we have no control over. So we just assume it's going to be whatever it is. But if I'm in design of experiments world, I control the x's, I do not control the variance. So I can use this formula, to try and minimize the variance of my slope estimate. Well, how do I do that? Well, if I'm in a situation where my X values, let's say they go from negative 100 to 100, then what I do negative 100 and 100, each in equal parts, 50-50. That will spread everything out from that average as much as possible. If I can only do, let's say, range from 5 to 10, then half of them will be 5, half of them will be 10, and that will maximize this part down here. Now, if simultaneously I can figure out a way to minimize the sum of the squared observations, I can minimize the variance of the y-intercept. But usually we don't worry about this too much, just because, you know, we just kind of make the assumption most of the time that the intercept exists. So for hypothesis testing, we really don't worry about this too much. But if I was in the situation where I needed to minimize the variance, what I could do is, if I can kind of like make this into a more stable value and then minimize the sum of squares, I can reduce the variance. So I've got, for this one, I've got two aspects I could control if this is super important to me, which I can't see why I would, but it might be. Actually, you know what, okay, this is a nerd thing that I did. I took my skydiving data and to figure out the rate at which I fall while I'm under canopy, I use a linear regression model to work out what was the wind of the jump and what was the speed, and that way I have a better estimate of how fast I move, and I needed low variance on the y-intercept for that. So that was cool. To get the data, I use the Dakunu, by the way. If you're into collecting data, it's a good way to go. All right, so something to be mindful of in this formula is that the covariance is the opposite of the sign of x bar. Okay, so if x bar is positive, what is going to happen is that if, like, the slope estimate increases, the intercept estimate is going to decrease. They're going to go in opposite directions, and they're going to kind of like balance out. Be mindful about that. Let me see something. All right, so now we want to talk about the Gauss-Markov theorem. Remember, anytime a theorem has a name, it's a big deal. All right, so if you see something like mean value theorem, you know it's super important because it's just so, basically it's saying its property. It's so important, we just call it by its property name. The second most important theorems in mathematics and statistics are the ones where the person's name comes into it. We use it so frequently that we say the person's name. Okay, so if the expected value of y is x times beta, the covariance is sigma squared times I, then the least squares estimate of the coefficients has minimum variance of all linear unbiased estimates there are. All right, okay, so it's going to be best estimate. Yeah, we're going to call it, or it's blue. It's best least unbiased estimate. Okay, so what are we going to do? We're going to say that A is a matrix such that A times Y gives us a different estimate of beta. Okay, so why is this a reasonable approach? What I need to do, I need to back up. I'm going to go back up to the original part of the lecture. All right, look here. Look at this formula. To get my estimate, I'm taking a matrix and I'm multiplying by Y. I've got X transpose X inverse X transpose. All of the X terms in here, that is one matrix. So this is, then I take this one matrix, I multiply it by Y, that gives me my estimate of beta. Okay, so this is a matrix, a linear operation, times our observation of the target variable. Because it's matrix times target variable data is a linear estimate because we're doing linear regression, or sorry, we're doing linear algebra. All right, so what we want to show is that the formula using X transpose X inverse X transpose, that matrix has all these nice slick properties. It's blue. All right, so we're going to go ahead and we are only interested in estimates that have minimum variance and it's unbiased. All right, so what we want to do, so A is any. So at this point, we don't know what has minimum of all the unbiased estimates. We don't know which one has minimum variance. We're just going to say, I want to take any linear transformation. So it's linear. That means it's the multiplication with matrix. It's unbiased and it's minimum variance. So what we're going to do, I start out, I grab all the linear estimates that are unbiased. Okay, well, it's unbiased means that the expected value of A times Y is beta. Okay, well, A is a constant matrix. Therefore, the expected value of AY is equal to A times the expected value of Y. Okay, well, I realize that the expected value of Y by assumption is X times beta. Okay, now at this point, we don't know what beta is. So I replace expected value of Y with X times beta. All right, so I've worked out that the expected value of A times Y, it's unbiased, therefore it's equal to beta. I've also worked out, because of this other assumption, is that the expected value of A times Y is AX beta. All right, so these two have to be equal to each other because they're equal to the expected value of A times Y. All right, so I have this. Okay, well, X is full rank. Because X is full rank, the only way for this to work out, so if you think for a moment, if I subtract beta from both sides, then I have AX beta minus beta is equal to 0. Okay, if I factor out the beta, I have AX minus I, parentheses, beta is equal to 0. All right, well, this can work out, this can work for any possible beta. Okay, so since this works for any possible beta, this formula so far, because we didn't specify which model we're working on. Kind of interesting aspect of this proof. We didn't specify which beta we're working for, so this formula has to work for all betas. Since it works for all betas, the only way for this to work out, since X is full rank, is that A times X is equal to the identity matrix. Okay, well, let's keep on rolling with this. So we've got to this far. This is what we get from using expected value. This part of the proof, or this part of the assumptions and unbiased, get us this much. Now, let's start thinking about that covariance aspect. Well, the covariance of A times Y is A covariance Y, A transpose. By assumption, this is A sigma squared I, A transpose. Now, I remember that multiplying by a scalar is commutative, so I can pull that out front. And I remember that multiplying by I doesn't do anything. So in fact, the covariance of AY is sigma squared times A transpose. Okay. What I'm going to do now is I'm going to rewrite this because I'm interested in the difference between A and the formula that we have, because I'm trying to work out how do all the minimum variance, linear, unbiased estimates relate to the one that we've derived so far. So I'm going to take A, I'm going to add and subtract the X portion of our formula. I'm going to do it both ways. So I do it to A and I do it to A transpose. You notice I've got the T. This part of the formula corresponds to A transpose. And you'll notice I'm adding and subtracting the same thing on there, so I'm not changing anything. All right, well, here I just go through and I distribute the transpose. So remember that X transpose X is a symmetric matrix. Since it's symmetric, then its inverse is also symmetric. So when I go through and distribute, and remember, transpose changes the order on the matrices. So this is X times that inverse matrix, X times the inverse matrix, we're adding and subtracting. All right, now what I'm going to do is I'm going to take this part here, I'm going to put a parenthesis around it, and the same part, I'm going to put a parenthesis around it. Now what I'm going to do, I'm going to go through, I'm going to do multiplication. I'm going to treat this as a matrix, that part inside the curved parenthesis, and this part inside the curved parenthesis, and I'm going to leave this part alone, and I'm going to go ahead and do matrix multiplication. I'm going to use the distributive property of matrix multiplication. And I get all this junk. Now, when I work through this, a bunch of stuff cancels out. And since a bunch of stuff cancels out, I'm going to get rid of it. I go through, and I'm going to have a total of like 4 terms. Now remember, anytime I have A times X, that becomes the identity matrix. So this part here is the identity matrix. And then these two cancel out to be the identity. So I end up having X transpose X inverse, X transpose X inverse, one positive, one negative. It's out of there. Okay, now, this is, I've got X transpose, A transpose. That's the same as AX parenthesis transpose. So I know that this is the identity matrix. All right, this part and that part, they cancel out to be the identity matrix. So I have this, I have the X transpose X inverse, X transpose X inverse, one negative, one positive, they cancel out. And then here I'm left with this stuff, and these two cancel out. All right, so a lot of stuff is just like boom, 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 just canceling out for us. I'm left with this business. All right, so now, and this comes from multiplying the parentheses up here. When I multiply the parentheses together, I get this part. Everything else collapses down to that part. Now, let's think about it for a moment. I have a matrix times its transpose. If we remember, that's going to be positive definite. And this is going to be positive definite also. All right, so because of the whole positive definite aspect, the only way I can minimize this is if so the X is a constant value, constant matrix. Since the X is a constant matrix, there's no way I can minimize this. Remember, I want to minimize my variance. I'm trying to find all the possible linear unbiased estimates that have minimum variance. So if I look here, if I want to minimize the variance, then what has to happen is the stuff in the parentheses has to be, add up to 0. Because if it's 0, then that's going to disappear, and I'm going to get minimum variance. Okay, well, how do I get 0 in there? Well, A has to equal X transpose X inverse times X transpose. Once I have that, we see that the formula that we have, that we already derived, is also minimum variance. So this is a big whoop-de-doo. All right, another way to articulate the Gauss-Markov theorem is that if the expected value of Y is X times beta, and the covariance of Y is sigma squared times the identity matrix, then our least squares estimate is blue. It's best linear unbiased estimator. It's got 3 properties, and that's a lot. This is, if you think about your theoretical statistics course, your mathematical statistics course being best, linear, and unbiased, you get a lot of properties out of this. This is nice. Now, something to think about this is that we never said what the distribution of Y was. In fact, we never said what the distribution of anything was. We just said expected value and the variance and the covariance aspect. So we said that the expected value of residuals is 0. We said that the residuals have a constant variance with respect to X. And we said that the observations are independent of each other. We have not said anything about the particular distribution. Kind of interesting. All right, now, a corollary of this is that if I have these 2 assumptions and beta hat is from our formula, then a blue estimate of A transpose beta is A transpose times beta hat, which is nice. And basically, just to get that, we just have to work out a few details using the proof. It's very similar to what we've got. All right, now, if we select X so that the columns are orthogonal, and when I say orthogonal, that also means they're orthogonal to the constant vector, then we're going to minimize the variance of our estimates, and we're going to maximize the power of the test. Now, orthogonal is sufficient, but not necessary. So if I set up so that in my design of experiments phase, I have orthogonal vectors, then I'm going to have this. It's possible to minimize the variance with and maximize the power without being orthogonal, but this is the easiest way for us to get it, honestly. Now, the next thing, the next proof, basically, this is just saying if I transform my observations in a linear manner, so I'm using matrix multiplication, then my modeled values of y will not change. Okay, so if x is equal to this vector, z is equal to a similar vector, just that we're hitting each variable with a constant, then y hat will be beta hat transpose times x. It will also be beta hat transpose of z times z. Now here, beta hat sub z is the least squares estimate when I apply that formula to z, the z matrix, instead of the x matrix. All right, how do we prove this? What do we do? Well, I look at this and I realize that I can represent z as a diagonal matrix times the x vector. All right, so the z vector is d times the x vector. Well, I can represent z as x times our data matrix times the diagonal matrix. And so then I take the z formula for beta hat sub z and I just work out the details with a plug and chug. It's beautiful. And I see that when I plug it in, I'm just replacing z with this business. Well, remember that diagonal matrices have like special commutative properties which make things a little bit easier for us. Actually, I don't need that. I scratch that, retract that. That's wrong. All right, remember when I have an inverse of matrix multiplication, and everything has an inverse in there that's inside the, if I have multiplication of 3 different things and I take the inverse, it's going to be switch the order and take the inverse of the individuals. All right, so if I take the inverse on this, this is going to be this d, inverse goes there. The inverse of the x transpose x goes here, and then the inverse of the transpose of d. Okay, now, diagonal matrix means that it's symmetric. Since it's symmetric, d transpose is equal to d. And that's just d. So I have d inverse times d. So that cancels out as the identity matrix. And so I see that all this business becomes a formula that we're used to. So that's just beta hat. So now it's d inverse times beta hat. So I can see the relationship here. And that gives us a formula so nicely. All right, so what does this tell me? If I use this part right here, that d transpose z times z is equal to beta hat times x, these are equal to each other. Well, this is how I get my y value, my modeled y. This is how I get my modeled y. If they're equal to each other, then it doesn't matter which version I use, which model I use, is it the x model or the z model. Either way, I get the same modeled values of y. Okay, so what we see here is that if I do full rank linear transforms on our predictor variables, I get the same values of modeled y. This is a big deal. Why is this a big deal? Because this enables me that, let's say I want to go through and I want to center and scale my predictor variables. Well, when I do that, I can center and scale my predictors. It's not going to change my modeled values. This is something that I personally do when I'm doing machine learning. Also, if I do principal component analysis is a linear transformation. It's a full rank transformation. Therefore, I'm not going to change my modeled y values if I use all of my principal components. This is very nice. This is a very handy thing for, let's say if I'm in machine learning and I want to do variable screening. Something I personally do when I'm screening variables is that I'll take I'll center and scale the predictors, and then I'll start doing my linear regression models. And why do I like this? Because in that situation, my coefficients are proportional, will be proportional to my t-value, as long as my variance inflation factor is not huge. All right, so that means that I can look at the coefficient rather than the t-test statistic to be able to judge, is this a useful, is this a useful predictor? Also, if I see that the standard error of the t-test is getting is bigger than the others, then I can be worried about variance inflation factor very nicely. It helps me screen things very easily. I can be lazy. Also, our S-squared estimate is invariant under the scale transforms. Our R-squared, our regular vanilla R-squared will be invariant under scale transforms. And our F statistic will also be invariant under scale transforms. So that's very nice. All right, well, that's all I've got for you. Take care and goodbye.